Hi everyone, it's Mrs. Summer again. I'm here to talk about lesson 105, the rules for electron configuration. In this lesson, students will be able to model an atom's electron configuration using quantum mechanics, apply the AFBA Principle, Hund's Rule, and the Paulis Exclusion Principle to fill atomic orbitals. Remember that the quantum mechanical model describes the probability of finding an electron within a certain volume of space surrounding the nucleus. It doesn't tell you the exact location, but just the chances of finding an electron. And it does explain the quantum numbers. So how exactly do we explain the quantum numbers in the quantum mechanical model of the atom? We use orbitals and energy levels. The energy levels of an electron are labeled by principal quantum numbers n. Each energy sublevel corresponds to an orbital of a different shape, which corresponds to a different shape, which describes the probability of where an electron is likely to be found. The shapes are labeled by letters. The letters are S, P, D, and F. The letters don't describe the shape. So what that means is that just because it's in an S orbital doesn't mean the orbital looks like an S, or an F orbital doesn't look like an F. The orbitals have a specific shape that we will go over in a next couple of slides. So the orbital shapes. The 1s orbital is a sphere directly surrounding the nucleus. It tells you that the electron is in the orbital closest to the nucleus. The s orbital can hold at most 2 electrons. After the 1s orbital, the 2s orbital is very similar to the 1s. It's just slightly further away from the nucleus, but it's still that sphere shape, and it still can only hold 2, I need to delete that one. It still can only hold 2 electrons. The p orbitals come after the 2s orbitals. So the first energy level, there is only the 1s orbital. After the 2p or 2s orbital, the 2p orbitals, they look like dumbbells and they're in 3 directions. So because they're in 3 directions, they can hold at most 6 electrons. So the p orbitals, 6 electrons. The s can only hold 2 electrons. The d and f orbitals, the d orbitals has 5 directions, which means it can hold at most 10 electrons. Drawing my little electrons here. And then the f orbitals has 7 directions, 1, 2, 3, 4, 5, 6, 7, and it can hold at most 14. So if you notice, if it however many directions it has, you multiply that number by 2, and that's how many electrons it can hold. Electron configuration is a detailed way of showing the order in which electrons fill around the nucleus. So we have here, the 1 that comes in front of that 1s2 is the energy level. So what is the energy level that it's in? The sublevel then is the s. So this is in the 1s energy level and sublevel, and this exponent of 2, that is the number of electrons in the sublevel. So we know from this electron configuration that these electrons are in the 1s and with 2 electrons in the 1s orbital. In order to fill, we must follow 3 rules: AFBA's Principle, Hund's Rule, Paulis Exclusion Principle. If you look over here, this is just a neat chart of how you fill. So we start here and we fill going the 1s, then we start back up here, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so forth. So you fill your electrons going that way. And how we know how many electrons to fill is based on what we learned a couple lessons ago with however many electrons a neutral atom has. So the first principle is the AFBA principle. In this principle, electrons occupy energy levels with the lowest energy first. It means that you're going to fill the 1s orbital before you fill the 2s. You're going to fill the 2p before you fill the 3p. If you look on this little chart, so we fill as the energy levels increase, we go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, just like that handy dandy diagonal chart we just saw. That's what the AFBA principle is. It just means that you're going to fill the lowest energy first. Hund's rule. It states that electrons that occupy orbitals of the same energy level will have the maximum number of electrons with the same spin. That means that its nickname is the empty bus seat rule, or like I would like to call it, the COVID-19 rule. It means that as you're boarding a bus, and there's an empty seat here and an empty seat here, this person comes on, they're going to sit here. And then another person comes on. If the seat's empty, they're not going to sit next to a complete stranger. They're going to sit at an empty seat. Electrons are the same way. Electrons have a negative charge. Well, what you've learned in physical science is like repels like. So the electrons are going to be pushing against each other. They don't want to be close to each other unless they have to. So the empty bus seat, you're not going to sit by a complete stranger unless you absolutely have to. Or in our world today, the COVID-19 rule, you're not going to stand next to basically anybody unless you absolutely have to. So if we look here, this correct way of filling this orbital, you have the 1s orbital, so there's 2 electrons in the 1s, because that's the 1s energy level. They have to pair up. The 2s is the same way. They have to pair up because the AFBA principle said we have to fill the lower energy levels first. Now we get to the 2p. Well, there's 2 electrons that we can fill. Over here, the incorrect, there's an empty bus seat over here. Empty bus seat, empty bus seat. So these electrons are going to fill this empty bus seat first before pairing up. Paulis Exclusion principle states that 2 electrons have to occupy the same energy level. They must have opposite spins. So in this case, this electron is going to spin up while this electron is going to spin down because they have to share the same space. Think about it this way. If you have a complete stranger, one person's going to be in that bus, this person's going to be looking out the window, and this person's going to be looking out the aisle. They're going to be as far away from each other as possible, even though they have to share the same bus seat. The scientific reason or the chemical reason why they spin differently is that, again, electrons have a negative charge. If both electrons in an energy level are spinning the same way, they'd experience too much repulsion and be unstable. It would cause the atom to be unstable. Here's an example of a question you might get. Fill the electron energy diagram for the electron configuration for oxygen. Then write the electron configuration for oxygen. Oxygen has an atomic number of 8, which means there are 8 electrons in a neutral oxygen atom. So we're just going to start. We filled my 1s, so that's 1, but now I have to put it down. So 1 spinned up, 1 spin down. So now I've filled 2 electrons, so I have 6 electrons left. So I'm going to go to the next energy level, AFBA's principle. I'm going to fill 1 electron spinning up, 1 spinning down, because that's 2s is the next highest energy level. So I've filled another 2 electrons. So I have 4 electrons left. So now I get to the 2p. Now, I'm going to apply Hund's rule and fill the 3 separate spaces for the p orbital with my electrons all spinning up. Empty bus seat rule. Now, I've used 3 more electrons. So I have 1 electron left. So now, I'm going to fill in with a opposite spin that other p orbital, because the p with 3 electrons still wasn't completely filled with electrons. Remember, the p orbitals can hold at most 6 electrons. So then they doubled up. To write the electron configuration for oxygen, I would start by writing my 1s. There are 2 electrons in the 1s orbital, so an exponent of 2. Then I go to my next level, 2s and 2, because there's 2 electrons in the 2s orbital. Now, for the p's, I have my 2p, and I have 1, 2, 3, 4 electrons in my second p orbitals. So the electron configuration for oxygen is 1s2, 2s2, 2p4. Here's a clearer picture than the one I just drew of the oxygen's electron configuration. Here's an additional example. Fill in the energy diagram for electron configuration for copper. Then write the electron configuration for copper. So if you notice, copper has 29 electrons in a neutral copper atom. So I filled my 1s2 twice. Then I went to 2s, 2p, 3s, 3p. Then I filled my 4s because the 4s has less energy than the 3d orbitals. And when I did that, I was left with 3d9. I filled every part of the 3d except for that last box. So the electron configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9.